Hello and welcome to our 10th and final lab of the semester, which is calorimetry and specific heat. So for this lab, we are again looking at the conservation of energy, trying to verify this law that our initial energy will equal our final energy. Again, we'll just have our energy change form, go from one to another. We're not creating or destroying energy. This lab, we are going to be using mixtures and seeing that this law will still apply. So in the absence of any phase changes, the amount of heat that we would need to change the temperature of an object of a particular mass from an initial temperature to a final temperature is equal to this formula. Our heat is equal to our mass times the specific heat of this of the mixture that you are looking at. For our lab, we're going to start with just water, basic H2O, times the temperature involved. So if we were looking to change a temperature, this would then become mass times the specific heat of our final temperature minus our initial temperature. Okay, so again, C here is our specific heat. It is going to vary depending on the particular substance or mixture that we are looking at. Luckily, when we're looking at the specific heat of water, this simply equals 1 calorie per gram degree Celsius. Okay? So when we see C multiple times in these equations, it's just going to be entered as 1, or it will become, because of its value of 1, like we saw in previous labs when we were using 1 kilogram as a mass, it's something that will not impact these equations. If we were using a different substance, as we'll see later in the lab for part 2, C becomes more significant. But luckily for us, because we are looking at mixtures of water and the specific heat of water is 1.0, this will make our calculation significantly easier. So when we're looking at our heat and our changes, if our quantity of heat is positive, our mass is absorbing heat from our setup. If our Q is negative, that means it has given off heat to its surroundings. So if, again, we have a positive Q, we would expect the temperature to increase. Negative Q, we would expect a decrease in temperature. So we're testing this theory in our lab by combining a known mass of warm water with a known mass of cold water. So we will know the mass of this water and the temperature of this water. Again, we're looking for the two extremes. One is going to be warm, one is going to be cold. We are going to combine them together and see our new equilibrium temperature. We would expect to see the temperature of our warm water decrease compared to our final temperature. And obviously, conversely, we would expect to see our temperature of our cold water increase when we add warm water to it. So using these known masses of water of two different temperatures, we can test this theory by combining these two values together. So we're adding mass, an unknown mass of our warm water to a known mass of our cold water, checking the new temperature, and seeing if we can apply what we know about the law of conservation of energy, that our initial energy should equal our final energy. Our heat loss should equal the heat gain. So again, our warm water is losing energy to get to this new equilibrium temperature, and our cold water is gaining energy to get to this final temperature. So we are going to compare these two values to each other. Okay, so because again we are in this remote format, these procedures have been done for you. We have taken known masses of both warm and cold water, combined them together, provided the temperatures of all 3 different cups, and you will then need to perform these calculations. Again, we're just looking at the mass of the warm water times our specific heat of water, looking at our change in temperature from our initial temperature of just warm water to our combined cup. And we're doing the same thing with our cold water. And we are hoping to see that whatever heat was absorbed by the cold water was lost from the warm water, making our entire system stay conserved. So whatever energy is lost by the warm water transferred to the cold water and vice versa. We're not creating energy, we're not destroying energy, it is just being transferred. Okay, so to test this, we will have a percent difference comparing our heat lost and our heat gain. So our Q loss to our Q gain. Okay? And hopefully we'll see that these are approximately equal, and we can in fact confirm and verify the law of conservation of energy as it applies to mixtures. Okay, this is part 1 of the lab. There will be a second video for part 2.